Hello everyone, my name is Yihan from the Hong Kong University of Science and Technology, Guangzhou. Today I'm excited to present our research semi-automatic layout adaptation for responsive multiple view visualization design. Here is the agenda. I will first introduce multiple view visualizations with small displays. As many of you might be aware, multiple views are frequently employed in visual analytics and dashboard to provide a comprehensive perspective on data. Our previous study, led by Chen in 2021, has explored the common design patterns of multiple view visualizations. We collected and analyzed the new dataset comprising 360 samples, which offers a fresh perspective on this subject. For the small devices, in recent years we have seen a surge in the use of commercially available mobile devices such as mobile phones and tablets. These devices have become increasingly popular for exploratory data visualization and visual communication. However, most of the multiple view visualizations we see today have primarily been designed for desktops. This trend presents a golden opportunity for multiple view visualizations designed to look beyond just a desktop environment, and there's a need to auto-adapted multiple view visualization designed on desktops to small displays. Existing works that support some basic adaptations for multiple view from desktops to small devices. Now I would like to show some of the existing tools and their common pitfalls. Many visualization tools offer auto-adaptation of multiple view visualizations. Here we take the ArcGIS dashboard as an example. It's a dashboard for COVID-19 analysis, and here is the layout of the desktop. For the mobile layout, they use tabs to show each view separately, and users need to click the switch between each view. Tableau took another approach by arranging each view vertically to fit small devices. Usually, user needs to keep sweeping down the screen to see all the views. So here I want to address some of the common pitfalls associated with existing methods. First, the scale and stretch method. While it might seem like a straightforward solution, it often distorts the aspect ratios of the visualizations, leading to a misinterpretations or loss of crucial information. Next is the vertical stacking approach. Although it can be effective in certain scenarios, it has the potential to alter the view topology, and this can disrupt the intended flow and hierarchy of the visualizations. Lastly, methods like horizontal scrolling or using tabs might seem user-friendly at first. However, they demand substantial user interactions, which can be cumbersome and distract for the overall user experience. Moving on to the next part, I would like to introduce our approach, focusing on design considerations and a two-stage approach, including layout, retargeting, and view tolerance. We begin by formulating the design space of multiple view visualizations. The visualization is seen as a composition of various views. Each view proposes a distinct mark type, such as bar, map, line, point, and pie. Each view has a unique view size. The position of each view forms the topology of the multiple view visualization. The display property is defined by dimensions, specifically width and height attributes. While it comes to interaction, apart from the basic interactions, we have incorporated link among multiple views. Overall, we transform this design criteria into declarative requirements. Next, we have distilled the key requirements and considerations from extensive prior work. At the heart of our approach are two non-negotiable hard constraints. First is keeper views. Every view in a multiple view visualization offers a unique perspective, enriching our understanding of data. Second, we must avoid overlap to prevent occlusion that can hinder data interpretation. Beyond this, we have identified the soft constraints that guided the design but requires a balanced approach. This includes avoid unnecessary extra viewports to keep the visualization coherent, minimizing white space for efficient space usage, maintaining aspect ratios to perceive the integrity of original design, perceive view topology, and ensure the view readability, especially on smaller devices. While our approach constraints are mandatory, Our soft constraints are conflict with each other and can only be balanced. For instance, if we want to minimize the white space, it's definitely to change the aspect ratio since we adapted the visualizations to a new device with a different shape. We have devised a two-stage method to address the challenges in responsive multiple view visualization design. Firstly, we have automatic layout retargeting. This involves a tree traversal mechanism for grouping views to viewports of small devices. Once grouped, we employed a simulated annealing technique to determine the optimal layout for the target device. This ensures that our visualizations are not only organized but also optimized for the specific display they have presented on. The second stage is view tolerance. Here, we prioritize the layout and the readability. We transpose certain views for better aspect ratios, such as we switch the views of X and Y channels to enhance the clarity. Font size adjust properly to the display space, and to combat clutter, we employ strategies like label rotation. Here is the demo of our system. Users can input data and then visualize it. Layout can be adjusted through dragging, and link views are applied. Users can adjust the view properties and appearance from the input panel. The control panel on the left facilitates display adjustment and layout changes. After selecting Convert, results are ready in a short time. We have adjusted space utility weights and tests with various datasets, like baby names for tablets and the streaming data for iPhone. Now I'd like to demonstrate some results generated using our system and the user study. Here we have re-implemented some examples from the tablet gallery and adapted them to small devices. We have used real-world data from top baby names in the US to daily COVID-19 status. Result: A1 to D1 are smartphones, and A2 to D2 are tablets. What can be observed is that we try to weigh the various design considerations as much as possible, such as in case D, we have always kept the small multiples together, maintaining the topological of the multiple views. Here is another example of visualization of Olympic medals and an example of the US election. These are also results generated through our approach. We have also conducted a comparative quantitative user study with 3 existing methods involving 15 participants. They are scale and stretch, vertical stacking, and horizontal scrolling. Participants started by familiarizing themselves with a multiple view visualization on the desktop. They then navigate through results from the 4 methods on both smartphones and tablets. After exploring, they rated questions like question 1 and 2, focusing on the consistency of layout properties between the original and adapted layouts. Question 3, which looks at the topological difference, and question 4, which is the ease of completing specific analysis task. Here are our results. In our experiment result, HS stood out in maintaining consistency in aspect ratio and relative size, with our method closely followed. While HS and SS achieved good performance in perceiving consistency of view topology, our method excellent in view readability. Most notable, participants find it easiest to complete analytic tasks using our method. Overall, our approach was the top preferred, trailed by HS, VIS, and SS ranking last. In the end, let me conclude my presentation. Responsive visualization is an area worth exploring. Our focus has been on responsive design trailed for multiple view layouts, and we'll consider more view types and properties in the future. We have introduced a semi-automatic method informed by the design space and considerations unique to multiple view visualizations. However, there's more to be done. We aim to delve deeper into user perceptions of multiple view visualizations, develop superior evaluation metrics, and address the computational speed challenges posed by simulated annealing. We believe a blend of automatic algorithms and semi-automatic tuning is the way forward for design tasks. And for those who are interested, our code is open source and available at the provided link. And thank you all for your attention today. If you have any questions or thoughts, please do not hesitate to reach out. I'm always open to discuss and collaborations.